Hi, welcome to Kinetics Part 3. My name is Dr. English. Today we're going to be talking about energy and chemical reactions. Specifically, we're going to be looking at introducing potential energy diagrams looking at the forward reaction, potential energy diagrams looking at the reverse reaction, heat of reaction, endothermic reactions, exothermic reactions, calculating heat of reaction. So let's start off by talking about energy and chemical reactions. What we need to first understand is the basics of a potential energy diagram. So when a chemical reaction happens, old bonds are going to be broken and new bonds are going to be formed. And that's a really important thing to remember, that when any chemical reaction happens, we're going to be breaking bonds and forming new ones. To break old bonds, energy must be absorbed. You have to put in energy to break something. To form new bonds, energy is released, because in the process of releasing that energy, it's going to become more stable, and therefore we're going to form those new bonds. As a chemical reaction proceeds from reactants to products, potential and kinetic energy changes will occur. These energy changes can be represented graphically by potential energy diagrams. Only potential energy is represented in these types of graphs. So let's look at a potential energy diagram and sort of break it down, the different parts. As two reactants approach each other, their potential energy is constant. And we can see that right at the beginning, right here. We see this potential energy over the progression of the reaction, and it's going to just be a flat line. As particles collide, their potential energy will increase. So this section right here is when the particles are colliding, and we see that increase in potential energy. They will reach a maximum potential energy when something known as the activated complex is formed. And the activated complex, and we'll talk about this a little bit more later, is an intermediate. It's not a reactant, it's not a product, it's very, very unstable, and we can see that represented as ABC right here. So this right here at the top of this little bump right here is known as my activated complex. So we'll represent that as an AC. As the activated complex breaks apart to form products, the potential energy will decrease. We can see that downward slope right here as energy is being released. So this energy is released. So that's what's happening right here as we go on and we form the products. So as we can see in this final bullet right here, new products are formed and the potential energy remains constant. And again, we see that constant potential energy right here at the end where we're with the products. So we start out with reactants AB plus C. We form an intermediate at something known as the activated complex, which is represented as ABC, and then we form our products, which is A plus BC. So this is the general components of one of these diagrams, where you start with reactants and you go to products. So let's look at the different parts of a potential energy diagram, and we're going to look at it from the perspective of a forward reaction. Now, what do I mean by a forward reaction? A forward reaction in terms of one of these diagrams is reading the diagram from left to right. So we're going to start over on this side, with this side being my left and this side being my right, which means that A right here is going to represent my reactants basically. So let's make a little note of that right here. So this is my reactant, and I'm going to B right here, which is going to be my product. So product. So we're looking at it as a forward reaction going from reactants to products. And what we're going to do here is we're going to label the different parts of this potential energy diagram. So what is number one? Well, one is going to be the potential energy, and I'm just going to represent potential energy as PE of my reactants. So potential energy of my reactants. Now, two is the activation energy of the forward reaction. And activation energy is just the amount of energy that you need to put into the reactant to basically break it apart or rearrange it so it can go on to be a product. So 2 here is going to be our activation energy. So activation energy. Now let's find 3. Here's 3, this whole huge big line going all the way down here. 3 represents the potential energy of the activated complex. So potential energy of the activated complex. And what that includes really is basically adding together your potential energy of your reactants plus your activation energy. So it's all the energy needed to get to the very top of the activated complex, which is right here. What is 4? Here's 4 over here. 4 is the potential energy of my products. So potential energy of my products, which is right here. And then finally is 5. And 5 is located right here. And this is an important one to know. And 5 is known as the heat of reaction. Heat of reaction. And ultimately, heat of reaction. Ultimately, 5 is going to tell us whether a reaction absorbs energy or releases energy. And we might be able to, if we're given numbers on our potential energy diagram, be able to put a numerical value behind whether energy is absorbed or released. So one way that you can look at 5, which we know as heat of reaction, or an abbreviation for that is delta H, is that it's the difference between the potential energy of our products minus the potential energy of our reactants, and we'll talk more about that. Here's a similar diagram, a couple little differences from what we just saw previously in the previous slide. And again, we're going to label the parts of a potential energy diagram, except in this case, we're going to be looking at a reverse reaction. So in this case, we're going to be reading from right to left. So I'm still going to call this is my left and this is my right, but I'm going to be read it in this direction. So all of a sudden, B is now going to be my reactant and A is now going to be my product. I'm going to be looking at this in reverse. So for here, if we start going through our numbers, let's look at number 1. Well, number 1 corresponds to our product. So it's still the potential energy of our products. Okay, because it's lined up with what we're looking at as our products. So it's the potential energy of our products. Let's look at 2. Now 2 is very interesting here because this is activation energy. Because ultimately, if we look at 4, if we jump ahead for a minute, we look at 4, we know that 4 is going to be the potential energy of our reactant, because we're going to call B here our reactant because we're going in reverse. So 2 is the activation energy of our reverse reaction. So if we were to look at this going from right to left, 2 would be our activation energy. So activation energy. And let's put a little note here, reverse, just in case you happen to look at this again and you're like, wait, why did she call that the activation energy of the reverse? And it's because we are going in reverse. We're going from right to left. Number 3 will still be our potential energy of our activated complex. So potential energy of our activated complex. And finally 5. 5 is still our heat of reaction. Heat of reaction, which again we're going to designate as delta H. And it is still the difference between the potential energy of our products and the potential energy of our reactants. So now let's talk about heat of reaction. Heat of reaction is identified as the quantity of heat energy either absorbed or released during a chemical reaction carried out at a constant pressure. Heat of reaction represents the difference in enthalpy or heat content, our delta H, between the products and reactants in a reaction. Enthalpy change. Now remember, this delta symbol right here means change. So delta H literally means enthalpy, because we know enthalpy is heat, because H in there compared to something known as entropy, which we'll talk about later. Enthalpy change is just change in heat. So enthalpy change is defined as the heat energy either absorbed or released by a system at a constant pressure. And like we said, it's represented by a delta H. Now, in order to calculate this delta H, we're going to take the heat of the products minus the heat of reactants. And typically it is expressed in kilojoules per 1 mole. Let's talk about endothermic reactions. Now, endo here can be thought of as in. So in. And thermic basically refers to heat. So an endothermic reaction is a reaction where heat is absorbed. So when energy is absorbed by a reaction, the potential energy of the products is greater than the potential energy of the reactants. So if we look at this little diagram down here, here's our potential energy of our reactants right here. Potential energy of reactants. And then some amount of heat is absorbed over time. So heat is absorbed, and then we get to our products. So this whole thing right here, going from the bottom all the way to the top, is the potential energy of my products. Now, in this process, there's more energy as products than reactants. Therefore, overall, heat is absorbed, and we'll find out that our delta H is positive, and we'll look at a calculation for that in a minute. Let's compare that to an exothermic reaction. Exo, you can think of exo as exit or released. Thermic, again, is heat. So this is a type of reaction where heat is released. When energy is released by a reaction, the potential energy of the products is less than the potential energy of the reactants. So in this particular diagram, my reactants, so I could put this all the way up to the top, so that's the potential energy of my reactants. That has a lot of energy compared to the potential energy of my products down here, potential energy of my products. The difference between these two is from here to here, which is represented by this delta H. But in the process of going from reactants to products, a lot of heat is released, and we're going to see that our delta H is negative when we look at calculations behind this. Calculating delta H from potential energy diagrams of endothermic reactions. All right, so we have this potential energy diagram right here. We have, this is our reactant, this is our product. We have our reaction pathway. So to figure out our delta H, we're going to take the heat of the products minus the heat of the reactants. So if I look at my products, that is 100 kilojoules. So 100 kilojoules. And we're going to subtract that from the potential energy of our reactants, which only goes up to here, and that is 50. So 50 kilojoules. So 100 kilojoules minus 50 kilojoules gives me a positive number, specifically 50 kilojoules. So my delta H is positive 50 kilojoules. Delta H in endothermic reactions will always be a positive number as energy is absorbed. Now let's calculate delta H from a potential energy diagram of an exothermic reaction. So we're going to do a very similar type of thing here. We have our reactants right here. We have our products right here. This is the potential energy of our reactants, and this right here is the potential energy of our products. So to figure out the overall delta H, we're going to take the energy of our products minus the energy of our reactants. So if we follow this line across, we see that we have 20 kilojoules minus our reactants, which is at 40 kilojoules, 40 kilojoules. So 20 kilojoules minus 40 kilojoules will give me negative 20 kilojoules. And all that negative means is that energy is released out into the environment. So the delta H here is negative 20 kilojoules. So delta H in exothermic reactions will always be a negative number as energy is released. And if you forget that fact, you can always go to table I of your reference table and read at the very bottom of the chart, there's a little asterisk that says endothermic reactions always have a negative delta H, because that whole chart deals with delta H values, which we'll talk about in future videos. Now what I'd like you to do is stop, do a little bit of practice, come back and check your work. Welcome back. Let's see how you did. So they give us this potential energy diagram to use with parts A, B, C, and D outlined. Base your answer on the reaction coordinates shown below. Which interval represents the heat of reaction? The heat of reaction. Now remember, the heat of reaction is going to be the difference between the potential energy of the products minus the potential energy of your reactants. And that's one of the first things that I would label on here. So delta H is equal to the H of your products minus the heat of your reactants. So automatically A and D are out, because A represents the potential energy of the reactants and D represents the potential energy of the products, which leaves us with the C and B. Now C and B are sort of in weird spots on this diagram. It could be really easy to look at B and say, oh, that's right above the potential energy of the reactants. I'm going to call that the activation energy. But remember, activation energy goes from the potential energy of the reactants all the way up to the top of the activated complex right there. So C is really our activation energy. B, on the other hand, represents right here the difference between the potential energy of our products minus the potential energy of our reactants. So in this case, B would be the correct answer. Let's look at another practice problem. So what I'd like you to do is stop, look at the diagram, read the question, figure out the answers to the two problems, then come back and check your work. Welcome back. Let's see how you did. The forward reaction is best described as an exothermic reaction in which energy is released, exothermic reaction in which energy is absorbed, endothermic reaction in which energy is released, endothermic reaction in which energy is absorbed. Classic question here. So the first thing that we need to figure out is whether this is an endothermic or an exothermic reaction. So here's the potential energy. Let's see, potential energy of my reactants right here. And this is the potential energy of my products right here. And I know that my delta H, which is going to tell me whether something is endothermic or exothermic, is the heat of the products minus the heat of the reactants. What you could do here, just as an arbitrary thing, is that you could actually assign numbers. So let's say this is 40. And let's say this is 10. And it doesn't have to be exact number, one has to be larger than the other. So I'd say the potential energy of my products is 40, and that's first, and minus the potential energy of my reactants, which is 10. So 40 minus 10 gives me 30, and it's positive, and I know that a positive delta H is an endothermic reaction. So that means B and A are out. It has to be an endothermic reaction, so one of these two. Let's look at the rest of the answer for both of these. Endothermic reaction in which energy is released, endothermic reaction in which energy is absorbed. Well, endo basically means in or absorbed. So the correct answer here is going to be D, endothermic reaction in which energy is absorbed. And we can see this based off of our diagram. The initial amount of energy of our reactants is low. We add in energy, and the final energy of our products is much, much higher. So we had to absorb energy to get to the products. So this is most definitively an endothermic reaction. Let's look at the other question. Which arrow represents the activation energy for the forward reaction? So remember, activation energy is the amount of energy needed to get the reactants up to the activated complex. So that means potential energy of the reactants is right here. So this is my activation energy, the amount of energy needed to get from this area right here to the top of the area right here. So my answer would be A. B is the potential energy of my activated complex. C is going to be the potential energy of my products, because that matches up right there. And D is actually the activation energy of my reverse reaction if I was going in reverse here. That's why in the question, they're very specific about saying forward reaction, because they list both the activation of the forward reaction and the activation of the reverse reaction right here. So don't get caught off guard by that type of question. So what did you learn in this tutorial? We introduced the concept of potential energy diagrams. We looked at potential energy diagrams from the perspective of a forward reaction and a reverse reaction. We talked about heat of reaction, endothermic reactions, exothermic reactions, and how to calculate heat of reactions, and then a little bit of practice at the end. Need more help? Feel free to contact me. Have a great day.